Hello and welcome student to the online lecture of course MA412 linear algebra, and this is lecture number 4. Lecture number 4. Yeah, so recall in our last lecture what we defined something called basis of a vector space with some 4 equivalent conditions. Okay. So the natural question is that how do you know this basis always exists, right? So if we have a vector space V, and then how do you know that a basis V always is V always contain a basis? This is a natural question to ask whether every vector space is a basis or not. Okay. So generally for finite dimensional vector space, the course answer is easy by there is something called Placement Theorem that I am going to discuss later. But let us first try to answer this question in general. What happened? I mean, we don't know whether this kind of set has finite living elements or not. Okay. So in general, how do you answer this question? So to answer these questions, we need to understand something called Joan's lemma. Okay. So this idea, Joan's lemma. This is we are going to understand this. So let me first discuss the tools which we require for Joan's lemma. So okay, what does Joan's lemma say? Joan's lemma says that if write down the statement first. If every chain of a poset has a maximal element inside that poset, okay, not inside the chain, element in the poset, then the poset has a maximal element. Then the poset has a maximal element. Now I have to so I will discuss what are the meaning of poset and other things. So what is a poset? Poset means partial order set. Poset. This means partially ordered set. Ordered set. Now, what does that mean? That means so you have a set. So is a set with a partial order on S, right? And partial order means what? Partial order means what is the meaning of partial order? I think you have done, but let me just recall again. partial order is what? So this is a relation satisfying three conditions. So relation must be reflexive and number two, antisymmetric. I hope you know this all definition. Otherwise, we will discuss this in our next this live session. Okay, symmetric. Number three, transitive. So if a relation satisfies these three conditions, then we call it partial order relation. Okay, and I said with one such partial order relation is called a poset. Okay, so now we understand what is a poset, but what is a chain? So what is a chain? So a chain. So there are two some people also call it totally ordered subset, but let me just call the chain. Okay, a chain in a poset is a chain. So let me write down, say like this: C in a poset, say something like P is a totally ordered subset of totally or okay. So let me write down. I will write down the meaning. Actually, this is a subset of P. That is what? That is for any if you choose any two pair for any A and B belongs to this chain C, we have either A relation. I don't know what is the relation, so let me write down this symbol, less than equal to B or B less than equal to A. Okay. So you can always compare any two elements of the chain. That's why it's called totally ordered subset. Okay. But in general, we know that in partial order set, we may not compare any two elements, right? If you compare, when you can compare in some subset of that partial order set, those subsets are called chain or totally ordered subset. Okay. So this is the definition, and then now you understood if you can compare these things, so this become a chain. Now if you choose every chain has a maximal element, so that means every element is this is kind of the upper bound, so everyone less than equal to this, then the whole poset has a upper bound. Okay, so you don't know which one is upper bound, but that tells you that the whole thing is upper bound. This is called a Jones lemma. Okay, so so now we are going to use it for proving that every vector space has a basis. Now recall that the way we define the basis, we define it by four conditions, right? Either condition 1 was linearly independent and spanning set, condition 2 was maximal linearly independent set, right? Condition 3 minimal spanning set, right? And condition 4 is the uniqueness of representation of any vectors, right? So here we are going to use that the second condition, the maximal, a basis is a maximal linear independent subset. For that we are going to prove a simple theorem, and that theorem gives us the existence of basis. What is the theorem? So let V be a vector space or linear space, whatever you write them, doesn't matter. Linear space, and you have a subset which generates actually V. So let and some G be a subsets that generates V. Okay, so that means span of G equal to V, span G equal to V. Okay, So if this is the case, then and then the, any like maximum independent subset. Okay, so okay, so yeah. So before that, so let me just give you one. I think main theorem. Let me give you one just obvious things. So if this is a subset of generating set, and then you can start with linear independent subset of G. So let then any linear or other I should say maximum linear subset. So this is already proved. So just let me write down here maximal linearly independent subset, linearly independent subset of G is a basis. This is already this is for G, right? Because so this is maximum subset inside if you are choosing G, so that will be a basis. So this is actually, and we want to show one more important theorem that whatever linear subset you choose, you can extend to a maximum linear subset. What does that mean? That means it's always contained inside a maximum linear independent subset. That is the theorem we are going to prove. That every linear independent subset of a vector space V contains inside a maximum linear subset of V. Okay, so every linearly independent subset of B contained in some maximum. So I don't know which one. Some maximum linearly independent subset of okay. So what does that mean? That means you can actually start with linear subset, and then you can actually extend to a maximum linear subset, right? And that is the basis. So what is the corollary? Corollary is that of this theorem will be what? That every vector space has a basis. Because whatever you start with the non-zero vectors, that will be linear, right? And then you can extend it. That will be inside some maximum linear subset, which you cannot even extend it, and that is nothing but the basis. So every vector space is a basis. The corollary. Now we have to prove the theorem. Then we will have done. Now to prove this theorem, we will use Joan's lemma. We need to use something called Joan's lemma. Okay. So let me start with a and say some linear subset. So proof. Let is be any linearly independent subset of V, right? So I need to prove that is actually contained in some maximal subset. Okay. So I and also I said that I am going to use Joan's lemma, so I need to find out a proper partial verset, right? So what is that? So I'm just finding this. So P is collection of all linearly independent subset of V containing S. So we collect all such subsets which contain S, right? And obviously this is non-empty, so this P, this is non-empty, as S actually belongs to, right? S belongs to P. Where is continuous and is also linearly independent, right? So I have a collection P, which is collection of all linearly independent subset of this V continuous. Now I need to give a partial order structure on this set P. So what is the relation? So this inclusion, simple inclusion. So we define the partial order relation order on P by inclusion of sets. Of sets. What does that mean? That means so you choose two sets. So that is you say A subset of A less than equal to B if A is included inside A subset of B. Okay, this is the relation. Okay, now you can check that this relation is actually partial relation. This is automatically reflexive, antisymmetric, and transitive. Okay, simple. So by P is a partial order set, that is obvious. Now what I need to choose? I need to choose that I need to prove that if every chain has a upper bound, then I will Joan's lemma tells you that the whole thing is upper bound, right? Now how to prove that every chain has upper bound? So it's arbitrary chain. So let C be any chain in the partial set P, right? So I start with the chain P. We see inside P. Now how do you show that C has a upper bound in P? Upper bound means maximum element. Okay, in P. So how to prove that? So we need to show that C has a maximum element in P. Okay. So what is my claim? So my claim is that let you choose U be the union of all elements of C okay. So my claim is that U is that element. So claim U is the U not the U is that U is a actually is the so this is maximal. Okay, so this is maybe more than one. U is a maximum element of of C in P. Okay. Now one part is obvious. Every element of U should contain, right? So that is obvious. So note that U contains every element of C, because U is the union, right? So U contains every element of C. Okay, but we don't know whether U is inside P or not. So that is, we need to check whether U is a so element of C, and hence the ace is also inside U, right? Ace is inside U, that is obvious, because C is inside, C is the collection of elements inside inside P, and P contains all the linear subset which contains S, right? So S inside U. But how do you know that U, the way I collect that thing, that is also linearly independent? I don't know, right? That we need to check. Now we need to say that now we need to find out that whether U is a linearly independent subset or not. So U contains, that is obvious. Now to check something is linearly independent, what we need to check? We need to check that so this set may be infinite. So I don't know. So to check something is linearly independent of infinite set, what do we check? So for any finite collection, that has to be linearly independent, right? So if states R is the finite collection, so let some U1, U2, some belongs to U, and the constant something C1, C2, Cm. Okay, so these are the constant inside the vector space, the scalar field of the vector space F. Okay, so the original vector space V is over some field F, right? That field. Now such that you collect those things such that the sum over Ci Ui I equal to 1 to M, that is 0. Okay, this is given to you. Now I need to prove that all the Ci's must be 0. Okay. But before that, you check that this U1, U2, Um are element of U, which is the union of all elements of C. So what does that mean? That means every element U1, U2, Em will be inside some element of C, right? So again as U is the union of Ci's. Okay, so there are too many Ci's, so let me write down some different symbols. Maybe AI's belongs to C. There exists some A1, A2, AM inside C, such that what happened? This UI is an element of AI. That means U1 inside A1, U2 inside A2. I'm just numbering this. Okay. UM inside AM, right? Some numbering. And we choose such a way that A1, see, this is chain, right? So so out of that there will be one element which will be contains everything, right? Chain means what? That any two things is compatible, right? So out of n many elements there will be something biggest one, right? So A1 and A2, the A2 is containing A1, then A2 and A3 is maybe A2 containing A3 again, then A2 A4, maybe inside A4, like that. So there is the biggest element, right? So as C is a chain, there exists some AK such that all AI's is subset of AK, right? For all I equal to 1, 2 and n, right? and this implies this all the ui's are element of AK for all I equal to 1, 2 and n, right? But AK is a element of P, and hence it actually contains all linearly independent elements, right? All independent, so AK is a linear subset, so elements are AK is a linear independent, right? So what does that mean? That means this U1, U1, U2 and UK, UM is linearly independent as AK is so. So AK is linearly independent, so every subset of linear subset is also linearly independent, right? So this U1, U2 is linearly independent. Now once you have linear subset, and then if you just have this kind of equation, sometimes Ci ui equal to 1 to n 0, and that will obviously so maybe this is equation star. So thus from star, from equation star, what we have? We have the Ci's are 0, right? For all I. Okay, so that is we want. So all the Ci's are 0, and thus that proves what? That proves that this U is linearly independent, right? What we want. So we want that that maximum element inside the poset, right? So this is linearly independent. So thus, thus using Joan's lemma, we have a maximal element for the poset P, right? So what does that mean? So the P was containing linearly independent subset which contains S, right? And hence that S also contains some maximal element. So thus let's say S contained in some maximal linearly independent set or subset, whatever subset of V. Okay, so this is the proof, and that has to be a basis, the maximal subset. Okay, so that now the corollary tells you that every vector space is a basis, right? Okay, so now this is the existential proof. But in general, how do you like what is the case for finite dimensional space? So that can you actually start with a linear independent set and can you make a basis? The answer is yes. And we need to know something called replacement theorem for that. So let me discuss this here. Replacement theorem. Okay, so what does replacement theorem tell? So it tells that let V be a vector space with a generating set or spanning set, whatever. Okay. Spanning set so G and um, so G maybe with okay, so G and A. So I'm assuming that V is fine dimensional. Okay, I'm just assuming V is fine dimensional because yeah. So and linearly independent set L. Okay, then this cardinality of L is always less than equal to cardinality of G. Okay, and if we just assume that say cardinality of L equal to say M and cardinality of G equal to say N, suppose this is the assumption, then and you can have something more, and there exists a subset H of G such that L union H actually is a generating set, so that generates the vertices V with how many elements? With H has coordinate of H is exactly n minus m. Okay, so what does that mean? That means from a generating set you can have a new generating set. Inside that you have some part of linear independent subset is there sitting there. So you can replace a generating set by a linear independent set. That is the theorem tells you. Okay, and that is corollary actually. I am going to discuss that also. But you can replace one of the each element from the generating set by a linear independent subset. Okay, this is the theorem tells you. And the proof is also depends on something called mathematical induction. So the proof is so we'll use this something called principle of mathematical induction. Induction will give the proof. Okay, so what is that parameter where we want to use the induction? So we'll use the induction. We'll use induction on the cardinality of A, which is nothing but M. Okay. Now what happens if M equal to 0? So if M equal to 0, so what does that mean? There is no linear independent subset we are choosing. So that means that L is actually empty set, right? And then obviously current of M is less than equal to current of G, right? Empty set. Then H you choose, then H equal to G will give the proof. Because M is 0, n minus m equal to n, so you can choose H equal to G. Give the proof. Okay, so now we'll assume that you have at least one element, right? So m greater than 0. So thus so mathematical induction, you know that you have to assume that something is true, right? So what is the something called induction hypothesis? So it's called induction hypothesis. Next part, induction hypothesis. What is that? So we assume that it is true for at least some m which is greater than 0. Okay, so suppose the theorem is true for some m greater than 0. Okay, for 0 obviously is obvious, right? So we have now, so this is, we assume it, so now we have to prove that it is also true for m plus 1, right? So thus so you start with a set, let L be a linear independent set, so L equal to something, so you choose some vector, say v1, v2, vm plus 1, b a linearly independent subset of v, right? Now I need to check that, first I need to show that your L is actually the coordinate of L is equal to coordinate of G, right? Now how to show this thing, and this is one, and second thing is that there will be some elements which if we attach, then L union that set will be the generating set, right? So this is given to me. So if something is linear independent, then any subset of that set is also linear independent. So then this v1, v2, and vm. So if you choose this is a proper subset of a linear independent subset. So thus this is also linear independent. So now you can use the induction hypothesis, right? This is true for m. So thus using induction hypothesis, we have, what do we have? We have m has to be less than or equal to n, and you have another set containing n minus n many elements. So let me write down that u1, u2, and u n minus n, and this will be a subset of G such that there exists this such that this whole thing, like v1, v2, and vm union these u1, u2, u n minus m. So this whole thing that generate v, right? The span of that is v. Okay, so this is the induction hypothesis tells you. So what does that mean? If this generate v, so that also generate that element v m plus 1, right? This is also element of the vector space v. So thus v can be written as some linear combination of these vectors, where will be m u1 into un minus m, right? So we can write something, say alpha vi I equal to 1 to m plus some beta ui, and here I equal to say 1 to n minus m, right? That is this coming from the definition that these vi's and ui's are generating the full set, and hence v has two of this form, right? Now what are the possibilities? Can m equal to m? The question, can n, so now note that n cannot be equal to m. If n equal to m, then what happens? As in that case this is v m plus 1. In that case, this b m plus 1 will be linear combination of v1 to m, and that contributes to the fact that L is linear independent, right? In that case, this v1, v2, and vm plus 1 will be linearly dependent, right? So which is a contradiction, because this is the L, right? Which is a contradiction. That is obvious. Now what happens? Can all those beta is also 0? The same thing. The beta is also cannot be all 0. In that case also, similarly, all beta i's cannot be 0. Okay, because in that case also L becomes linearly dependent, right? So now without loss of generality, assume that at least one of the beta is non-zero, say beta 1. Okay, so without loss of any generality, any T. So assume what I need to assume. We want to assume that this beta 1 is not equal to 0, and then you can write down u1 in terms of this, right? So thus you can write u1 in terms of other element, right? So what are the other element? So this is Vm plus 1 is there, and then minus summation alpha I vi's are also there, I equal to 1 to m, and those vectors are multiplied by so maybe I will multiply later. Okay, so yeah, so later, and minus summation beta I ui, now I equal to 1, not 1 to 2 n minus 1, n minus n, right? And then you multiply by 1 by beta 1, because beta is not equal to 0. So this is the u1, right? So that means u1 can be written as linear combination of v1, v2, vm plus 1 and u2, u3, u n minus 1. So what does that mean? That means you can replace u1 by vm plus 1. That is the important thing. Instead of v1, you can now input vn plus 1, because that you can replace, right? So what does that mean? That means that's why it's called replacement theorem. We are replacing a general vector by a linearly independent vectors. Vm plus 1 is a linearly independent vectors. Okay. So so what does that mean? That means that new set thus is, if you choose h equal to u2, u3 and similarly un minus m, then you see that L union H will be what? That will be V1, V2 and Vm plus 1, and union of this, right? Union of this, that u2 to un minus m, right? Now you already know that u1 is replaced by vm plus 1, and you already know that this set, well, yeah, so this set generate the whole thing. Okay, and if you replace this by another one, that doesn't matter, right? So what does that mean? That means this the span of L union A is so that contains actually span of the previous one, v1, v2, vm union u1, u2, u n minus m, and which is nothing but v. So that means the span of this content v means what? That means that is equal to actually v, right? V, the whole vector space. So that we just find out that this is the thing. And not only that, you have only one more thing. So what is the improved observation? You saw that n not equal to m, right? So what does that mean? That means n minus m is actually positive. So that also implies that m less than n, and this implies that m plus 1 is actually at least n, right? And that is obvious. So now this is the cardinality of L, which is less than equal to cardinality of G, which we want, right? So this implies cardinality of L is also less than equal to cardinality of G. And also you note that what is H? Cardinality H. Cardinality H equal to n minus m plus 1, right? Minus 1. There is one less element, so that means this is n minus m plus 1, right? Because H has element till u2 to n minus 1, um minus 1, so which is nothing but n minus m minus 1. So this is the element, right? This is exactly matching. Okay, so this is the proof of the theorem. So that tells you that you can replace generating some generating factors by linear factors, right? And that tells you that so what are the corollaries? So corollary of this is simple. That tells you that so what we learn? We learn that whenever a generating set is given, that number of elements is always more than equal to the element of the linear dependent set. Okay, and also we learn that every linear subset of V can be extended to a basis. So this is considered corollary, simple corollary, that every so I'm assuming that finite dimensional obviously linearly independent subset of V can be extended to a basis of V, right? Because it's a basis means also generating set, right? And if you start with a linear set L, then we know that this coordinate is equal to this coordinate. We just prove it. It makes sense, right? So so now what does that mean? That means you can find out some H which is inside B such that L this generates the full vector space, right? Full vector space V. Not only that, this cardinality is same. Cardinality of this is actually same as cardinality of V. Okay, so that also. Okay, so let me prove one more thing, that every if it has a basis, then it has same number of elements. Obviously, for final limit vectors. Okay. So that tells you that. So I will prove that every basis inside the finite dimensional vector space has same number of elements, which is we call dimension. So dimension is always unique. Okay, dimension is unique. We are going to prove it. Okay, so that tells you that you can actually extend L with some element to a basis. Okay, that will be same. Okay. Now, so this fine last one, let me prove it. And this is another corollary. I should prove this first, that every dimension is unique. Okay, so how do I write down? So let V be a vector space with a or having with finite basis, then every basis has same cardinality. Then every basis contains same number of vectors. Then every basis contains same number of elements. Right? So So proof is also simple. So suppose you have two bases. You start with say B1 and B2. Then you assume that so B1 is also linearly independent subset, right? If something is linearly subset and B2 is a spanning set, then replacement theorem tells you that this cardinality is less than this cardinality. This is one equation. But also B2 is also linearly independent subset and B1 is a spanning set. So you can use replacement theorem to say that this is less than equal to this, hence they are same. This cardinality are same. So this is simple proof. So you use replacement theorem twice. Once you assume B1 is a linearly independent subset and B2 is the spanning set, other one is the opposite one, and then you are done. Okay. Okay. So this is some brief idea of vector space. In fact, one can also ask what happens if some subspace has what happened to the subspace. So if the vector space is finite-dimensional, subspace is also finite-dimensional. Okay, and not only that, if a subspace is there with the same dimension, that has to be the full subspace, meaning that has to be the same vector, right? This is a simple observation. We can easily prove those things. Okay. And maybe now I'm going to stop with this. Okay. Bye.